Good morning, everyone. I don't have the need to introduce Emmanuel again. You all met him already. So Emmanuel, without further ado, you're most welcome to share your screen and deliver your lecture for today. And I will keep admitting the latecomers. Yeah.
Thanks.
Here we go.
Okay. Let me try get everything on one screen. Otherwise, it's a bit confusing. Okay. So you can see the slides, right?
Yes.
Okay.
We can also see your slides at the bottom. Maybe if you have a way to go on full screen for the actual slide that you're discussing, we would see it a little bit bigger. Or
yeah, I think it might be sharing the wrong screen.
Now we see some Python code.
Okay.
Yeah.
That's worse. Okay, let's try this one.
Okay, that's perfect. Yeah, that's much better.
Is it,
that's even better.
Great.
Perfect. Thank you very much.
Great morning, everyone. And this will be a gentle and maybe not too gentle introduction to machine learning. We'll see how it goes. But I just want to focus on fundamental ideas. I don't want to dive too deep into certain things because what I would like is for us to move into convolutional neural networks relatively quickly before the end of this series. So we'll start off by talking about some terminology and then some simple methods. We'll talk about the simple, I like to call it the smallest Lego in the building block of neural networks. We'll talk a little bit about how to train these neural networks and some of the things that can go wrong. And then we'll transition into the idea of feed-forward neural networks and deep learning. Okay, so yeah, actually, let's watch this video. I'm not sure how my screen is going to react, so let me try to just get this. Okay, so hopefully you can see the YouTube video. So this game is, I don't know if you've ever played this game before. I definitely did many years ago. And you have this little paddle at the bottom that you can control using some keyboard or some input device. And there's this little ball that bounces. And the goal of the game is to break all of these blocks. And the score is here. So when you break one block, your score increments by 1. So actually, this is when it's doing quite well. So initially, it's just playing randomly, and and you can see that the paddle is not hitting the ball sometimes. And then we train the model some more, and then the model gets a little bit better at playing the game. It's breaking more blocks. It's still not perfect. And then we train it some more. Now it's better. And then eventually it learns an interesting strategy, which requires less effort on its part. So what it learns is that if it can get the ball behind the blocks at the top, then the paddle doesn't have to move as much. So now it's got the ball at the top and it's just maximizing score. This is a nice example of machine learning in video games. So this is a nice strategy that the algorithm has managed to learn. So I usually like to show this because it's a fun example. And then another great example of machine learning is in this movie AlphaGo. I think you can watch it for free now on YouTube. Before you had to watch it on Netflix, but I think now it's on YouTube. If you haven't watched this movie, I would recommend watching this movie. It's a nice documentary on the game of Go, which is a very complicated game, and the number of combination of moves is massive. And the video is a little bit about, I guess, the human struggle of accepting defeat towards an algorithm. It's a nice movie to watch. But so the point that I'm getting at is nowadays machine learning is really just in nearly every application domain, in medicine, in ecology, in physics, in language processing, speech, Google, the voice translation, Siri, all these voice translation models are all using machine learning. So it's a great thing to learn about machine learning. It's going to be around for the foreseeable future, for many years. So it's a good skill to learn. So let's go into some basic terminology first. So the very basics is that we need a data set. So in our case, we'll be talking about supervised machine learning, but I'll go a little bit, I'll explain what that means. So in our case, we need some data set, and a data set will be made up of features, which will be the columns, and the examples, which are the rows. So an example of data will have multiple features. And typically in a supervised machine learning problem, we'll have a class or a target. And this is the column that we're trying to predict for. So in other words, what we're trying to do is to build a relationship between the feature space and the target space. So you can think of machine learning as just a functional mapping between the feature space and the target. So that's what we would like. Given some features, we would like to have a machine learning algorithm that can predict for the target. So how you would go about this is you would obtain a data set, and obtaining the data set is very time consuming. If it's a new area, let's go back to the theme of passive acoustic monitoring. Collecting the data can mean, having your microphones out for 6 months. So it's a very time consuming process. It involves purchasing hardware, sensors, maybe you're collecting data off the internet. It's not a step to be underestimated. It actually is probably one of the most time-consuming steps in this whole pipeline. And to clean your data as well. But once we've got our data set, we need to split it into training and testing. Then we train the model on the training data, and we evaluate it on the test data. So that's just the high-level picture of what we're trying to do. So when we have our whole data set, what we would like to do is split the data set into maybe 3 splits. One is the training data, and then you'll see that we have some validation and testing data. Now, why do we need validation and testing data? Why do we just not need training and testing? Well, so most machine learning algorithms will have these things called hyperparameters, and what a hyperparameter is just it's values that the human must tweak to try and get optimal performance. So these are decisions that humans typically make to try and produce a good model that can map between the feature space and the target. But if we train our model on the training data and then we evaluate on the test data, So you should think of the test data as next week's data, next month's data, and you should think of the training data as last week's data or last month's data. So the reason for a test data is because we want to know how well the model will do in the future. We don't want to build a model on historical data and then see how well it did on historical data, because this is data that was used to create the model. We want to evaluate the model on data that was not used to create the model to see how it will do next week, next month. Is the model going to give us good results? The problem with only having training and testing is that these hyperparameters, these parameters that we're going to be tweaking, if we are tweaking it on our data that we are testing it on, then we're actually cheating, because then we are using our future data to optimize our model. So that's a bad approach. Instead, what we can do is we can train the model on the training data and then evaluate it on some validation data. And now we tweak the parameters a little bit, and we repeat this again. We train the tweaked model on the trained data and evaluate on the validation data. That was our second model. Now we tweak the model some more, and we repeat this process many times until we are satisfied with the performance on the validation data. When we're satisfied with the performance on the validation data, then we apply it on the test data, because now it's fair, because we only execute on the test data once, because the test data is like future data. So then I suppose there are some questions as to what should be the sizes of these splits. Typically, you would have as much data as possible in training, but you want the validation data and the test data to contain quite a bit of data as well. And let's take an example. Let's say you have 100 data points and you train your model on 99 of those points. And then you take the single data point as your testing data and you evaluate it. And by some statistical chance, let's call it that, your model gets the right answer by some luck. Now you say, wow, my model got the one thing right, 100% performance. But statistically, that is not very robust. What would be better is if your test set was fairly large, like maybe 10,000 examples, because then the statistical chances of getting all 10,000 things right by luck is quite minimal. So if you have a data set with 1 million data points, then training on 950,000 points is perfectly fine, and testing on 50,000 is fine, because it's not likely that you get the 50 examples right just by some luck. So there's a huge discussion around this, but just to keep things simple, we can say we'll have 80% for training, 10% for validation, and 10% for testing, provided that the testing set has, not a small amount of data, maybe 1,000 examples. So now there's two main types of supervised learning. One is classification and one is regression. So the top pictures represent classification, where we're trying to map the feature space into discrete targets. So for example, we have a feature space and we want to say these features are characteristics of a bird, or maybe a chicken, or a rabbit, or a cat. So we're trying to bucket things into discrete categories. Regression, on the other hand, is when we're trying to map the feature space into some numerical space. So we're predicting numbers. So essentially, they're two different problems, and the models we use will be different. So classification, for example, on the left is when we're trying to create a line that can separate two different things. So we want to separate the circles from the plus symbols. Regression is when we have data and we're trying to fit a line to the data. So two distinct problems, and the models and the approaches we use to solve this will be different. So let's talk about very simple building blocks. So in machine learning terminology, the feature space, our input data, will typically be called X, and then we'll have some model. It could be a fancy model, it could be a super simple statistical model, and this model will produce an output. You know, if it's a classification problem, it will predict the classes. If it's a regression problem, it will output some numbers. And we call the model predictions y hat. So what we want to do is we want to compare the model prediction y hat to the correct values. And the correct values are typically denoted as y. So X is our features. We put our features into our model. Our model produces the predictions y hat, and we compare the predictions to the correct values y. The correct values are sometimes called ground truth, or the true values, the correct values. The terminology doesn't really matter in this case. Okay, so let's have this simple problem where we would like to build a model, a simple model that will allow us to determine whether or not we admit a student into a course, for example. So we have the grades, the student grades, and we have some test grades. And we want to separate the red circles from the blue circles. So we can build a line that says if you're below the line, then you're not allowed into the course. And if you're above the line, then you are admitted into the course. So what we can do is we can create a simple line in the form, and this line is in the form of 2x1 plus x2 minus 18 equals 0. So this is the equation for this line. So we can rewrite the expression and say that the admittance score, so the score is 2x1 plus x2 minus 18. And if the score is greater than 0, we accept the student. So in other words, if it's above the line. And if the score is less than or equal to 0, then we reject the student. So this is our simple model. So here's our equation again, 2x1 plus x2 minus 18 equals 0. And we can express it in the forms of w and x's. So we can say that we can rewrite it as w1x1 plus w2x2 plus b equals 0. In this case, w1 is 2, w2 is 1, and b is minus 18. So this is just a different way of writing this, this one above. So given our w1x1, w2x2 plus b, we can have a short form. We can just say capital W x plus b equals 0. So it's just a different way of writing it. So our model prediction, in this case, y hat. So remember, the model predicts y hat. So what we could say is if our model will produce a 1, and let's say we agree that 1 means accept if wx plus b is greater or equal to 0. Otherwise, we output 0, which would be reject if wx plus b is less than 0. So this is our simple model. So what we have so far is we have our feature space, in our case, the x1, x2 coordinates. Here I wrote xy points, which plugs into some model, which we haven't exactly defined our model yet. And this will produce some y hat, which will be 1 or 0. It will be 1 if wx plus b is greater or equal to 0, and it will be 0 otherwise. So this is generally what we have so far. But what if instead of just having grades and tests, what if we had an additional feature like the rank of the student? So now the data would look like this, where we have the grades, the class rank, and the test rank. And now we don't have a line anymore, we have a hyperplane. And this is our hyperplane to separate the blue circles and the red circles where we accept or reject a student. So in other words, all we're doing is we are expanding our wx plus b because now we have a third feature. So we can say that the w1x1 is the test, w2x2 is the grade, and w3x3 is the rank. So we can expand and we can keep on adding more and more features. The only result is that our expression just becomes a little bit longer and it has more w's and more x's. So if we had a data set that looked like this, where we have feature 1, feature 2, feature 3, and so on and so forth until feature n. So now we have n features and we have our target y. We can expand wx plus b. So it will be w1f1 plus w2f2 plus w3f3, so on and so forth, until wnfn plus b, and that's the expression, right? So we can have as many finite number of features as we want, and the result is that we just have a longer and longer expression. So how does this link to neural networks? So I'll introduce the perceptron, which is the smallest building block of the neural network. If you think of Lego, you can think of the perceptron as one piece of Lego. And this is the structure of the perceptron, where all of our inputs in our data will come in here into the left. And then we have these weights, and the weights attached to this output unit. So we'll have as many input neurons as we have inputs. So if we have 10 features, we will have 10 input units. If we have 100 features, we will have 100 input units. And each of these units are connected to this output unit, which is the model output. So we say that this is a fully connected. So every unit on the left is connected to the unit on the right, and there is no connection between units in the input. So our inputs come in here from the left, and each of the edges between the input units and the output units has a weight value. So for those of you who have studied graph theory, you've probably seen graphs that look like this before, where we have units, we have the nodes and the edges that connect the nodes, and there's values associated with the edges. But in neural networks, the inputs come in here, and then we have these weights, and the output y hat is here. So how can we write our student little equation that we had into a perceptron? So what we, maybe you can think about this for 10 seconds. What do you think the values of these question marks are, given our expression that we've been talking about so far? So this is the test node. This is the grade node. I haven't introduced this yet, but maybe you can think for yourselves what you think these values are. And I'll give you 10 seconds to think about that. Okay, so here is the answer. So here you can see that test has a value of 2 associated with it. So here's our input for test, and here is the weight of 2 that is associated with test. Grade has a value of 1, even though I didn't explicitly write the 1. Here's our input for grade, and here is the value of 1. And here is this intercept, and it has a value of -18, and the value of -18 is here. So what the bias does is it acts like an intercept. So if you think back to high school maths, where you learned about y is equal to mx plus c, c was the intercept. It's the same idea with neural networks. Is we have an offset that allows us to shift the graph, just like with y is equal to mx plus c. And this is called the bias. This input has a constant value of +1. These nodes will not have constant values. This will be the actual value in the data, but this node has a fixed value of +1, and we just assign the value of the weight to this one. So here is how we can write our expression that we talked about before in this simple neural network format. So now what I can say is I can now make this unit, which is the output of the model, into the model we've been speaking about this whole time, where if the value is greater or equal to 0, we want to output a 1, otherwise we output a 0. So this essentially is our complete model. So let's take a look at how this, if we wanted to plug in some data points, let's see if our model works. So in this case, let's try the 0.95. So x1 is equal to 9 and x2 is equal to 5. So we are saying test is 9. So we're saying we're putting in a 9 here. And then we're saying grades x2 is 5. So we're putting in a 5 here. So 9.95 is here, and 0.33 is here. So let's see if we do the calculations, if the actual model will produce the same answer, because from the graph we can see that 9.5 is an accepting point and 3.3 is a rejecting point. But let's see if we put the same data into the model, if it tells us accept or reject. So how we would do this is we would have our data set that has our features, and let's plug in some data into our model, and let's do a calculation. So if x1 is -31, we put in -31 into here, and then we say -31 times -3. So that's this part done. Then we put in the value of x2, which is 40. So we say 40 times 2. And then there's no more features. So then we add the bias. So we say +1 times 4. So the complete expression would be -31 times -3 plus 40 times 2 plus 1 times 4. And that will give us our first value of y hat 1. So remember, y hat is the model predictions. So if you did that, you would get a value, and then you would ask yourself, is it greater or equal to 0? And then we can make a prediction for the second example. So we put in 22 here. So we'll say 22 times -3. And then we'll put in this value, -72 times 2 plus 1 times 4. So the full expression is 22 times -3 plus -72 times 2 plus 1 times 4. And then you ask yourself, is that greater or equal to 0? So note that what I can do as well is I can write the weights in a vector column. I can write my weights as -3, 2, and I can write the bias as a scalar as 4. So my weights is a column vector -3, 2, and my bias is a scalar 4. So what I can do for my first instance of data is I can write that as a vector -31, 40, and then I can write the weights as a column vector -3, 2, and the bias. So essentially, y hat 1 can be expressed like this: -31 times -3 plus 40 times 2 plus 4. Likewise, the second example, all I need to do is I just plug in the new values: 22 times -3 plus -72 times 2, finally plus 4. So in other words, we can express the weights as a vector, and we can express the the feature values as a vector as well. So now actually the calculations can be expressed via matrices, and that's very good for a reason that we'll explain later on. So this is how we obtain the values y hat, which are the predictions. Is we just multiply the inputs by the corresponding values of the weights, and we add everything up. But in this case, we had two features, test and grade. But can we generalize? Can we generalize to more features? So yes, we can. What if we had n inputs, x1, x2, x3, all the way up to xn? Then remember, each input has a corresponding weight. So x1 will have a corresponding weight w1, x2 will have a corresponding weight w2, x3 will have a corresponding weight w3, so on and so forth. And xn, which is our last input, will also have a corresponding weight wn. And of course, there should be a bias. I didn't draw the bias here. So then our model becomes wx plus b, is that greater or equal to 0? So we can write it as just the sum of wi xi, where I is equal to 1 up to n, plus b, and we're asking ourselves, is that greater or equal to 0? Now this thing here actually has a name. In this case, we were asking ourselves the question, is it greater or equal to 0? And the process of asking ourselves, is it greater or equal to 0, which produces an output, is known as an activation function. And the activation function we've been using so far is the step activation function. If the input is less than or equal to 0, then the output is 0. And if the input is greater than 0, then the output was 1. So that is a step function, because we were asking ourselves, was wx plus b greater or equal to 0? If it was less than, we were outputting 0, but if it was greater than, we were outputting 1. So this is an example of an activation function. So if we have our data again, now we can compute the values of y hat using our activation function. And at the bottom here is the expression. So what we want is our model predictions y hat, and that is equal to f, which is our activation function, which acts on wx plus b. So we compute wx plus b, and then we apply f, which is our activation function, onto this. In our case, f is the step function. So how would it work? Let's look at the first one. So we would say minus 31 times minus 3 plus 40 times 2 plus 1 times 4. We would do that calculation. And then we would say, is it greater or equal to 0? If it's greater than 0, we output a 1. If it's less than a 0, we output a 0 because of our function. The same for the second instance. We would plug in the value. So we would say 22 times minus 3 plus minus 72 times 2 plus 1 times 4. We would get the result. Whatever that result is, we now put we put that into our activation function. And for the step function, it says if the value is greater than 0, we output a 1. Or if the value is less than 0, we output a 0. Okay. Are there any questions about this? So there was a question about why does the bias have its own node? So the bias allows us to shift the function. So if you think of the expression y is equal to mx plus c, what does the c do? It allows us to shift the function. So the bias acts as the intercept. It allows us to shift the function. Are there any questions? Maybe
I think Emmanuel, Isaac raised his hand. Isaac, please, you're welcome to ask your question.
Please, mine wasn't a question. I just like the explanation about the biases, so I just give thumbs up. Okay.
Can maybe you just give a thumbs up if you're okay?
Okay, thanks.
So everyone, if you can just give a thumbs up, and then I can see if you are okay. Okay. So yeah, sometimes the thumbs up disappears, but it seems like I've seen quite a few thumbs up. So okay. So if there's a problem, you can interrupt.
Yeah, please have a
question. So now, pardon me?
I have a question.
Okay.
Yeah, I would like to know under what condition will you have to use the step function?
Okay, so my next slide is going to address that issue.
All right, thanks.
Okay, so now, we've seen how we can input data into the perceptron, and then we've agreed that we do the calculation wx plus b, and then we take a function and we act on wx plus b. Now we have a problem. We have a problem because when I input the data into the perceptron and then I apply the step function, my output is going to be 0 or 1. But the target value in my imaginary data set was 9 and 13. So in other words, whatever values of the weights I have, I will never be able to produce a value of 9 or a value of 13 because I'm using the step function, and the step function forces the output y hat to be 1 or 0. So we have a problem. We have a problem, and we want to try and fix that. So it turns out that there are many activation functions. So Isaac's question was under when would we use the step function? You might use the step function if, actually you would probably never use the step function in the real world. So let's just say that. The step function was originally proposed many, many years ago when researchers were looking at logic gates where values were 0 or 1. But in modern neural networks, we don't use a step function. We use different functions, such as hyperbolic tangent, the sigmoid, ReLU, and there's many of them. And actually, a nice research question is, can you discover new ones? So that's a fun question. So let us have a look at some of these different activation functions. So this was the step function, which was constrained to outputting values 0 or 1. Here is the sigmoid function, which is also constrained to 0 or 1. Actually, I didn't write 1 here, but this is the upper limit is 1. So the upper bound is 1 and the lower bound is 0. ReLU, on the other hand, is an interesting function. If the input is less than 0, then the output is 0. But if the input is greater than 0, then the output is a linear function. So we can see how ReLU might be able to solve this problem, because now we would have values that can approach 9, right? Because if my input is 9, then the output is 9, since this is a linear function. If my input is 13, my output is 13. So ReLU would somehow allow us to get these values. Sigmoid would not, because sigmoid is bounded between 0 and 1. So we need to think about our choice of activation functions with respect to the target. Perhaps the target is bounded between 0 and 1, in which case we can use sigmoid. Otherwise, you can also use a linear function. So if the input is less than 0, the output will also be less than 0. So depending on the target and the range of values of the targets, we might want to explore different activation functions. Okay. So now I want to talk a little bit about how do we allow the neural network to train. Before we discuss training, we need to discuss an important thing, which is the error function, the loss function. So our network is producing values y hat, but we have true values which are denoted as y. So we need some kind of function that will map between y hat and y. So you can think of an error function as a distance function. How far is the model output from the correct value? Is the model output very far from the correct value, or is the model output very close? So you can think of an error function as a distance. How far is the model from the correct value? Okay, so here you can see my lovely artistic skills, where I have drawn a mountain, and this is the blue sky, and this is the ground, the green ground. And this mountain has a name. It's called Mount Everest. So the mountain is about the error, so it makes sense that we call it Everest. And let's say that you're on this mountain and you start off at the peak, right? Now, let us pretend that the higher you are on the mountain, the more mistakes you're making, right? Because it's Mount Everest, the higher you are, the more your error. And the lower you are, the less error you're making. So let's say we start off here. Our goal is to somehow go down this mountain and to reach the ground. So this is where the optimal place to be, and this is the worst place to be. So what you can think of machine learning. So here, ML, machine learning, uses this error function to take steps towards the goal. Our error function tells us how far we are from our goal, but by using this error, we can go down, and we can guide our approach in going down this mountain. So let's look at this classification problem where we want to build a line that separates the circles from the crosses. So here you can see that the model is making 3 mistakes. It's classifying, let's say if you're above the line, you should be a circle, and if you're below the line, you should be a cross. So here, this cross is wrong because above the line are circles and below the line should be crosses, but we have 2 circles. So essentially the model has made three mistakes. Now, our model is a straight line, but we could draw another straight line which makes the same 3 mistakes. And we can draw another model between this data that also makes 3 mistakes. So this is a little bit of a problem, and we need to try and find a way such that if we have different models, we are accurately able to find the mistakes. In this approach, where we're just looking at counting the mistakes like this, we have no way of determining if a line drawn this way or a line drawn this way, which one is better, because they all will make 3 mistakes. So we need to devise a smart way of measuring classification mistakes, because this way is non-optimal, because however many lines I draw in this area, I'm always making 3 mistakes. So I have no way of measuring, is this line a little bit better than that line? So remember, the goal of the error function was to see how good the model is doing. We described it as like the distance, how far are we from the correct value? So we need a smart way to determine how good is the model. Is it a little bit better than what it was before? And this is the discussion we're going to have right now. So let's consider this question. Can we convert discrete targets into some integer space? So let's say we have a binary classification problem where we have 2 categories, a cat class and a bird class. One thing we could do is we could say the cat is 0 and the bird is 1. That's easy. But what if we have multiple classes? What do we do? What do we do then? Do we just have 0, 1, 2? And that becomes a little bit of a problem, because we don't want the model to think that the numbers have numerical meaning. In other words, we don't want the model to think that 2 is bigger than 0 or that 1 is less than 2. So we need to have a smart way of dealing with how we're going to represent our targets such that we can have good comparisons, and such that the model doesn't think that there's numerical meaning in the target. So one way of doing this is to one-hot encode the data. And what one-hot encoding does is it looks at how many different types of targets we have in our data, and it creates an equal number of dimensions. So here we have 3 targets. So the dimension of our vectors is 3. And what we do is we put a value of 1 in the position that the item occurs in. So we can encode all values of bird as 1, 0, 0, all values of cat as 0, 1, 0, and for this one, 0, 0, 1. So we can, in other words, we can convert the discrete targets into vectors. So we can have many classes in our target, but instead of numerically calling them 0, 1, 2, 3, 4, which would be a problem because then the model might start associating a numerical order, we can create these vectors. So what if we had 10 classes where the numbers were between 0 to 9? So class 0, class 1, class 2, all the way up to class 9. We can also do one-hot encoding. So we can say 0 is now a vector where we have 1 and we have 9 zeros. 1 is 0, 1 and 8 zeros. 2 is 0, 0, 1 and 7 zeros. And finally, 9 is 9 zeros and then a 1. So this is just a process of one-hot encoding. So how would we one-hot encode if we had these targets in our dataset? 2, 1, 2, 0. So we only have 3 unique things. So our dimension of the vector should be 3. Actually, maybe just take a minute and write, or just write on a piece of paper, or think, how would we one-hot encode? How would we one-hot encode this? What would 2 look like? What would 1 look like? What would 2 look like again? And what would 0 look like? And you can just think about it for a few seconds. Okay, so we have 3 unique classes in this data set. We have 0, 1, and 2. So the dimension of the vector should be 3. And this is one way of encoding it. We could say that 0 maps to 1, 0, 0, 1 maps to 0, 1, 0, and 2 maps to 0, 0, 1. So this process of converting discrete targets into these vectors is known as one-hot encoding. And this step is an important step to allow us to build an error function that will help to evaluate how good or how far we are. But it will make sense when we get there. This is the first step in the process. Are there any questions about one-hot encoding? In terms of how we create these vectors, or is everyone happy with the process of one-hot encoding? So one-hot encoding is simply converting discrete things into vectors. Can you maybe just give me a thumbs up if you're okay with the idea of how we go from discrete things into one-hot encoded vectors?
Okay, there are the thumbs up.
Great. Okay, so so far what we know is we know how to convert the discrete targets into these vectors. But we still don't know how we're going to measure the error or the loss. So we still don't know how the neural network will know if it's doing a good job or a bad job. And this is what we're going to move on to next. How can we know, how will the model know if it's doing well? In other words, a distance function from how far is the model from the good values, or is it doing very badly? Okay, so there's 2 main cases. The first case is when we have 2 classes, and case 2 is when we have more than 2 classes. Let's talk about this. So the question is, in the case of 2 classes or more than 2 classes, what should happen here in the network? What activation function should we use? How many units should be here? So these are some of the things that we need to think about, and we'll answer that. So in the case of 2 classes, what we can do is we can have a single unit. Okay, so we can have a single output unit, and we can have a sigmoid activation function. The sigmoid produces values between 0 and 1. And what we can say is we can define a threshold of, say, for example, 0.5. And we can say if the network output is less than 0.5, then the network is producing a class of 0. And if the value is greater or equal to 0.5, then the network is outputting a value of 1, in other words, class 1. So we have a 2-class problem, 0 or 1. So we can use sigmoid, and if the network output is less than 0.5, we map it to 0. And if the output is greater than 1, we map it to 1. So this is slightly more easier. There's less complications. We can have a nice threshold function, and we can map to 0 or 1, and we only need 1 unit. So this is in the case of 2 classes. Things become a little bit more messy if we have, in case 2, where we have more than 2 classes. So what we want, and this discussion is going to lead to this, is we want a way for the model to output some probabilities. In other words, if I input some data and I have more than 2 classes, we would like the model to say that there is a probability of some value that this input belongs to this class. There's a probability of some value that this input belongs to another class. And there's a probability associated with each class. So here is an example of the 3-class problem where the outputs are cat, fish, or dog. So let's say we input an image into the neural network. And what we would like is for the network, let's say we input an image of a cat. What we would like is for the network to have a high probability for a cat and low probabilities for the other 2 classes. So this is what we would like, for the network to be able to output probabilities based on the input it is receiving. So here you'll notice that the values add up to 1. If it doesn't add up to 1, then it doesn't make sense anymore. But if the values add up to 1, we can think of these as probabilities. So what we want is to devise a way such that the network can output values between 0 and 1, such that the sum of the values is equal to 1. So when I input some data, the network will output, in this case, if we build a model on 3 classes, for each input that I provide, it will provide 3 probabilities, and that we want these probabilities to add up to 1. So how can we modify the network to output 3 things in the case of a 3-class classification problem? So what we can do is we have our inputs as usual, maybe n inputs. And for a 3-class problem, we have 3 output units. 1 unit for each class. In other words, if we have 3 classes, this unit is the y hat for class 1, this unit is the y hat for class 2, and this unit is the y hat for class 3. If I had 10 classes, I would have 10 units in the output, 1 for each of the 10 classes. So in other words, each of these units, what we would like is for them to output an associated probability, and that the sum of these outputs is equal to 1. So in a 3-class problem, we would have 3 units, and we would like the network to output probability values. Is everyone still with me on this explanation so far? We will now discuss how this ties into the picture of the Onehot encoding. So we are slowly getting there. Can you give me a thumbs up if you're still with me? Okay. Okay. Let's take a small step. So let's say we have our model, which has n number of inputs, and it's a 3-class classification problem. So we have our 3 units, and we can write the network output as a column vector. In other words, this unit is outputting a value of 2, this unit is outputting a value of 1, and this unit is outputting a value of 0. So I'm just assuming that I've fed in some input and the model is producing these values. So I feed in some data, like an example of data. This unit is producing a 2, this unit produces a 1, this produces a 0. In other words, how did we get the 2? It's by saying Wx plus B. So we'll have all these connections, Wx plus B. This one will do Wx plus B. This one will do Wx plus B. And it gives us these values, 2, 1, 0. Okay. Now, our network output y hat produced 2, 1, 0. But the true value y was, maybe it was a picture of a cat. And remember that we decided that we were going to encode the cat as 0, 1, 0. Now, the network has produced 2, 1, 0, but my correct value is 0, 1, 0. Now, it's quite hard to compare these two things. So remember, what was the idea of the error function? It was to calculate the distance. How far is the network output to the correct value? Let's say we're going to subtract and take the absolute value. So 2 minus 0, 1 minus 1, 0 minus 0. So we would say 2 plus 1 minus 1. But what if instead the network output minus 2? So now we're saying minus 2, minus 0, and then we take the absolute value. So you can easily run into a problem where comparing these values just doesn't make any sense. And we need a smart way to compare these values. So this is what the network produced. This is what I wanted it to produce. I wanted it to produce 0, 1, 0, but it's producing 2, 1, 0. And comparing these values just by subtracting the numbers doesn't make sense. So what I would like is the values produced by the network, I would like to convert them into probabilities. So the network produced 2, 1, 0, but I would like it instead to produce these probabilities where a high value is associated with, for example, a high probability. So how do we convert these Wx plus B values into some probability? So this is what we would like to do. So one thing that we could do is we could take the value and divide by the sum of the values. So 2 divided by 2 plus 1 plus 0. 1 divided by 2 plus 1 plus 0. 0 divided by 2 plus 1 plus 0. Now this would, this is one option. can you think of any potential problems with this approach of just taking the value and dividing by the sum of the values? What would be one potential problem with this? Anyone want to take a guess? Why just, okay, addition of 0? Not quite. Probability of third category is always 0. Sure, that's a problem, but it's not exactly. So negative values would be a big problem. So if we, okay, so why would negative values be a problem? So what could happen that would cause this approach to not work? What about if we accidentally divided by 0? Right? So if this one was a 1 and if this one was a -1, then we would have 1 divided by 1 minus 1. So we would end up in a situation where we could actually divide by 0. So this approach of just taking the value and dividing by the sum of the values is not optimal because we could have an undefined operation. So this one wouldn't work because we would have 2 divided by 2 plus -1 plus -1. So it actually wouldn't work. And so our method wouldn't work. So yeah, essentially what I've shown here. So this strategy is not a good strategy. So how can we modify the method to get rid of this negative value? So what function can we use to convert negative values to positive values? There's many functions. So there are many functions exist, but taking the exponential will result in positive values. So if the input is positive, the output is positive. If the input is negative, the output is positive. So taking the exponent seems to be an interesting thing. So could we modify our approach by incorporating e to the x? So yes, we can. So what we do is we say e to the 2 divided by e to the 2 plus e to the -1 plus e to the 0. So it's the same strategy, except we're taking the exponential of each value. So in other words, the new function is, before it was x divided by the sum of x, now it's e to the x divided by the sum of e to the x. And actually this function has a name, it's called softmax. And now we don't run into the problem where we end up dividing by 0. Typically, I would ask you to do this. I would ask you to compute the softmax of these values. But I don't want to run out of time in this class. So maybe you can do this for homework, is just try to compute the softmax values of these values. So it would be e to the 2 divided by e to the 2 plus e to the -1 plus e to the 0. This one would be e to the -1 divided by e to the 2 plus e to the -1 plus e to the 0. And the last one would be e to the 0 divided by e to the 2, e to the -1, e to the 0. Now, if you took the time, you will see that ignoring some rounding issues, the values add up to 1. So this is great because now we are able to produce values that resemble a probability distribution. And that's what we wanted initially. we wanted a way to convert the network output into some probabilities. Is everyone still with me on this? So there are 4 more slides until all the pieces of the puzzle come together. We've talked about one-hot encoding and we've talked about softmax. Now somehow we need to put these 2 ideas together such that everything starts to come into place. So remember that we are on our error mountain, Mount Everest, and we start off in a bad place, and we want to go down the mountain. So we start off with a very high error, and we want to go down somehow. So now that we have the ability to compute a probability distribution, we now have the tools necessary to compute this error function. So remember, the error function, also known as the cost function, is what the machine learning algorithm will use to measure how good it's doing. And it will allow the machine learning algorithm to go down this mountain. So this is where we're going towards. So the loss function is used to measure the inconsistency, in other words, the error between the predicted value and the actual value. So how are we going to measure this loss? So how will the model know if it's doing a good job? So this is the fundamental question we're still trying to answer. How does the model know if it's doing a good job? So we can define a loss function, and the categorical cross entropy is a loss function that is commonly used for classification problems. So what it is we take the true value yi, we multiply that by the natural log of the predicted value for yi, and we will do this for each of the model outputs. So I is equal to 1 for m. So if we have m classes, there will be m output units, and we will have a model output for each unit, and we will have a true value from our one-hot encoding. So let's put this into practice. Oh, before I do my example, I want to just one thing I forgot to tell you, or I indirectly told you, is on this mountain, the higher you are on the mountain, the higher your error, and the lower you are on the mountain, the smaller your error. In other words, if our goal is to go down the mountain, then what we want to do is we want to minimize the error. So it's a minimization problem. Initially, you start off at the peak, you're at a very high error, and you want to go down, which is a low error. So this is a minimization problem. So a smaller error is a better value. Okay, so let's keep that in mind. So let's look at this little example where we have used softmax, and we have our network softmax values y hat, and we have our correct one-hot encoded vector. So these values were obtained using softmax, and these values were obtained using one-hot encoding. So in other words, the correct class in this case is this one. The 0 is not the correct class, and this 0 is not the correct class. The correct class in this case is this one. So let us use this cross entropy loss, categorical cross entropy, and let us compute the loss. Okay, so how does it go? We say 0, so it's the correct value times the natural log of the predicted value. So we'll do it row at a time. So this first 0 times natural log of 0.3 plus So there's a sum sign here. So we plus 0 times the natural log of 0.6, and then plus 1 times the natural log of 0.1. Okay. Now, since we have 0 multiplied by something, it's equal to 0. 0 multiplied by something is equal to 0. So the only part that we really need to focus on is this one, where we say 1 times the natural log of 0.1, and there's a negative sign in front. So our calculation becomes then minus 1 times the natural log of 0.1. So let's do that. So someone has done it, but if you didn't know how to do it, you can go on Wolfram Alpha, and you can just say minus 1 times the natural log of 0.1. Okay, so it's 2.30. Okay, so 2.30. Now, we have a loss of 2.30. Now let's take a look. Our model has produced a probability of 0.3 for this class. Our model has produced a probability of 0.6 for this class and a probability of 0.1 for this class. In other words, the model is quite confident that the answer should be this class because it's producing a large value for this class, and it's not too confident, or it's producing a low likelihood that it's this class. So we can see that what we wanted was for the model to have a high probability here. But instead, the model had a high probability for this class. Okay, so let's remind ourselves the loss in this case was 2.3. Now, instead, what if we have these softmax values where the model, the probability for this class is small, the probability for this class is small, but the probability for this class is now larger. Okay, now let's use categorical cross entropy again. 0 times the natural log of 0.3 plus 0 times the natural log of 0.1 plus 1 times the natural log of 0.6. So 0 times anything is 0, 0 times anything is 0. So the expression is then minus 1 times the natural log of 0.6. So let's go again on Wolfram Alpha and say minus 1 times the natural log of 0.6, which is 0.51. So now we can see that when the model produces a larger value for the correct class, we get a smaller loss. And our problem is a minimization problem. So can you see that when the softmax produces a larger value in the correct position, the loss is small, but when the model produces a small probability for the correct class, the loss is high. In other words, the model knows it's doing a good job when the probability with the associated class is high, and the model knows it's doing a bad job when the probability for the associated class is small. Are you all okay with that? Can you give me a thumbs up if you're okay with that? So in other words, we can now connect the idea of why we did Onehot encoding, why we use softmax, and if we use cross entropy, we can plug these two ideas together to produce a value that will tell us, or tell the model if it's doing a good job or not a good job. Okay, so I think I saw less thumbs up than before. So are there any questions about this? Is everyone still okay? Can we do the thumbs up thing again? I just want to monitor in this chat screen. Okay, so 3, yeah. Okay, people down here are not. Percy, Otto, Rebecca, Shane, how are you all doing? I'm not seeing thumbs up from the bottom group. Okay.
I don't see any. Ah, there is one.
Okay. Are there any questions? Does anyone have a question or confusion as to why this cross entropy is actually very good? Because we can see that it will produce a high loss when the softmax value is small with the associated class, and a small loss when the network produces a large probability with the correct class. Do you have any questions? Feel free to unmute. This is probably if this is the only thing you took from today's lecture, I would be very happy, because this is critical to appreciate this loss function. Are there any questions?
Hi, I have a question.
Yeah.
Can you hear me?
Yes.
I just want to know, why is it that on the Y hat you swapped around the 0.6 and the 0.1, but then on the Y correct you didn't swap around the 0 and the 1?
Because I just wanted to illustrate the difference. If we keep this constant, what different values are produced when the corresponding value to this 1 is different.
All right.
These ones we don't care because it's 0 times. These are the wrong classes.
Yes.
For this Onehot encode vector, what we want is for the value to be high. So that's why in the 2 examples, I kept this constant and I just shuffled these values.
Oh, okay.
Okay, are there any explanations? This is the most important, because this at least gives you an appreciation of how neural networks uses a loss function to know if it's doing a good job. Okay. If you have questions later, you can also post on the Slack channel. So now the very final piece of the puzzle that we have not answered yet, and for which I don't want to go in extreme detail, is how does the model improve itself? So remember initially, actually something I didn't mention is in my initial, in the neural networks, we have the weights. And the weights initially are randomly initialized values. And this is why we start off in a possibly bad location. If we knew in advance what the optimal weights were, then this would be a trivial problem. But we don't know in advance what the optimal weights for the neural network is. So we randomly initialize. And when we randomly initialize, we can start off in a bad position. So we could start off with a very, very bad loss. And then we need to optimize these weights. So the objective of neural networks is we start off with randomly initialized weights because we don't know what good weights are. So we randomly initialize them. And then we optimize the weights somehow, which I have not explained yet. So this is why I'm saying we start off with a bad loss. And the reason we start off with a bad loss is because we randomly initialize the weights. Because we have no way of knowing in advance what good weights are. Now, you might say, well, if you only have two features, then you can plot the error landscape by just plotting every possible value and having loss on the z-axis, and x and y would be every possible combination, and then you could visually see where the optimal solution is. Sure, if you only have two features, you could brute force and plot every possible value and find the optimal value. Similarly, if you only have one feature, you could plot every possible value and find the optimal value. But in the real world, we don't have one feature, we don't have two features, we'll have 10, 20, 1,000, 1,000,000. So we can't just plot the landscape and then find the solution. So we need to optimize the weights somehow. So far we've talked about the perceptron, which is the smallest piece of neural network. We've talked about needing to convert the targets into Onehot encoded vectors. We've talked about how to get the network output, and then how we can use softmax to produce probabilities. Then we talked about how we combine these two ideas and use categorical cross entropy to get an error. What we have not talked about is how do we use this error to update the weights? In other words, to optimize the weights to go down the mountain and find the optimal solution. So in other words, how does the network improve itself? So the network improves itself using a few things. The primary ideas is gradient descent, the learning rate, and the epochs. So my level of detail about this will not be extreme. And the reason is because I want to move on to convolutional neural networks so I can discuss the theme of this talk, which was machine learning for bioacoustics. But what I will do is provide the general idea. So let's say we have two weights. So we have a data set that has two features, feature one, feature two, and we know that each feature will have a corresponding weight, W1 and W2. So I can plot the error for all possible values of W1 and W2. I can plot the corresponding error. So initially, when I randomly initialize W1 and W2, maybe I start off here. I start off with a very high error. And what I would like is I would like to take these little steps and gradually go down and reduce my error until eventually my error is minimized. And this process is called gradient descent. So how do we update the weights? Is we say the new value of the weight is the old value of the weight minus a learning rate times the partial derivative of the error with respect to the weights. Now, this part here is messy, and I don't want to go into this detail. I can give you great resources, but for this series of lectures, I don't want to, because otherwise we're going to spend many hours just discussing this. So we take our old weight and then we minus a learning rate times this gradient. What does the learning rate do? The learning rate will control how big of a jump we make when we use the partial derivative of the error to compute the new weight. If we have a very large learning rate, then we're going to do a very big jump. So let's say we started off here and we have a very large learning rate. What we could do is we could take a jump and we could end up somewhere here instead. Or if we had a massive learning rate, we could take a big jump. and then we end up here, or we end up here. If we have a very small learning rate, then we take small jumps and we slowly go down the mountain. So the learning rate, which is a word that comes up quite a lot, is what controls the step size as we go down this mountain. Now, how do we go down the mountain is we take the gradient with respect to where we are to decide on the direction we are going to go in. So when we take into consideration how big of a step we take and the direction we go in, we can get the new value of the weights. So we take the old value of the weights, and then we take a step, and we go in the negative direction. So you'll see there's a minus sign here. So I will try to explain why we go in the negative direction of the gradient. So let's look at number 1. So this point. So the idea I want to illustrate here is why we go in the negative direction of the gradient, and why the negative direction of the gradient will allow us to go down the mountain instead of up the mountain. So we're here, we're at this dot, number 1, and this is a negative slope. So this is a negative gradient. So if we have a negative gradient and we take the negative of the negative gradient, that's a positive direction. The negative of a negative thing is positive, which means we move to the right. Positive means you go right. So here we have a negative slope, so it's a negative gradient, but our formula said we go in the negative direction of the gradient. So negative of the negative is positive, which means we go right. Now let's look at number 2. Point 2 is a positive gradient, and the equation said we go in the negative direction of the gradient. So the negative of a positive thing is a negative thing, which means we go left. So we're going to go leftwards. So in case 1, we're going to take a jump to the right, which means we're going to start here and we're going to jump down. We're going to jump this way, which means we're going down the mountain. But if we were at number 2, the negative of a positive gradient is negative, which means we go left, which means we take a jump towards the left, and we also go down. So this is an explanation as to why we take the negative of the gradient and not the positive of the gradient. So if we take the negative of the gradient, we will always go downwards. In other words, we'll go down the mountain, which is what we want to do. We want to go down, and gradient descent is about going down and minimizing the error. Are there any questions about this? So typically this is now when I would introduce the idea of backpropagation, but I don't want to do that because it gets very messy in terms of the chain rule, and it's extremely messy for multi-layer neural networks. But if there is interest, I can link you to lots of material. But if you accept that we update the weights using this formula, then I'm happy with that as well. We take the old weight and then we go in the negative direction of the gradient, and the alpha controls how big of a jump we're making. So is everyone okay with this? Can you just give me some feedback?
I see that thumbs up, Emmanuel. Emmanuel, are you giving a look at the time?
Oh, okay. So we've exceeded the time for today.
No, I'm sorry to mention this, but I have set up another Zoom meeting after 10:30. And if I'm still in Zoom, I can't start the other one.
Yeah, okay. So this is a great place to start. So thanks, everyone. We'll resume from here, I think, Monday. Yeah.
No, thank you, Emmanuel. Thank you very much. I think we had a lot of interesting comments, which means that our participants are active and paying attention. That's really very nice. And it was a lovely introduction to the Perceptron this morning. Thank you so much. That was really good.
Great. Feel free to ask questions on Slack.
Thank you. And just a reminder to the participants, at 2 o'clock today, we have part 2 of the statistics course. So please join us again this afternoon. That will also be very interesting. Thank you.
Great. Thank you, everyone.
Thank you, Emmanuel. And I will see you in 2 days. In 2 days on Monday.
Yeah.
Yeah. Wonderful. Thank you very much.
Thank you. Bye-bye.
Have a good rest of the day, everyone. Thank you very much. Bye.